Right, welcome back, grade 12. Now, let us look into Euclidean geometry. Now, for this question, I will give you 5 minutes to complete this question. Right, now, grade 12s, welcome back. Let us discuss the solutions to this question. Now, in this question, we are told that in the diagram, O is the center of the circle. And they say, use the above diagram to prove the theorem that which states that the angle subtended by the chord at the center equals to twice the angle subtended by the same chord at the circumference. That is to say, they want us to prove that this angle is 2 times that angle. So that means if this angle is x, then this one must be 2x. So that's what they want us to prove in that case. Now, so what is happening in this case? 2x here, then this is x, then that is 2x. Right, I go and write this time, yes. So this is the same. 2x, the angle at the center is twice the angle at the circumference. Now, so what are we supposed to do in this case? So what you're supposed to do in this case is the following. Now, given this diagram, the first thing that we need to do is the following. For us to prove this theorem, we are supposed to do what? We are supposed to have what? We are supposed to have 2 triangles. Now, how do we now have 2 triangles from this diagram? So, what we're supposed to do now is we are supposed to construct. So the construction for us, it will assist us to have 2 triangles. Why 2 triangles? Because you must notice that we must use the interior angle of a triangle to actually prove this. So there are 2 ways to prove it. So one of the ways is to do what? Is to use the interior angle of a triangle. It's equals to the sum of the opposite angles in the other segment. So now in this case, what we're supposed to do is the following. So construction will help us to have the 2 triangles that we need to work with. So what we're supposed to do there, we're gonna do what? We're gonna draw KO and produce it. So we're gonna just draw KO there nicely for us and produce in that way, such that this side is O1, this side is O2, and this one is K1, and this one is K2. So that is the construction that we made. Then why did you make that construction? It is for us to be able to prove that TOP is equals to 2 times TKP in this case. So what we're supposed to do in this case is the following. Now we proceed to say, okay, remember that these sides are equal. What makes them equal? It is what you call radii, because these are length, or these are chords that are drawn from the center. All of them that are drawn from the center to the circumference. So those are radii. We call them radii in that case. So what we're gonna say is the following. We're now gonna say O1, which is this angle. So it's equals to K1 plus angle T. So O1 is equals to K1 plus angle T. It's what is the exterior angle of a triangle. Like I said, we're going to use the exterior angle of a triangle to prove this theorem. So in this case, remember, when you have a triangle, as follows. So when you have that triangle, we know that this angle is equal to sum of those 2 angles in that case. So that's what we're having. We're saying O1, it is the sum of these 2 triangles. Right. So that is the first statement right there. Now, but we know that K1 is equals to K2. Remember, these are radii, these 2 lines, KO and OT. Those 2 lines are radii. So when they are radii, they are equal in length. So what we now have, we form an isosceles triangle, if you can check it. So this forms as an isosceles triangle. Now from this isosceles triangle, we know that these angles, the base angles, they are equal. So we're going to say K1, which is that one, is equals to angle T. What is the reason? Opposite angles, opposite equal sides. So it's angles opposite equal sides. So this is what we're saying. We have equal sides, then the opposite angles are also equal in that case. Right. So now this means to us, if you look at this one, we can now say, remember, our O1 is equals to K1 plus T. But we are saying K1 is equals to T. What does it mean? It means now, in a space of T, we can substitute T with K1. So we can just put K1 to that side there. So in such a way that we're going to have angle O1, it's equals to angle K plus, because T and K are the same, K1 and T are the same, due to opposite angles, opposite equal sides. Then we say K1 plus K1. Then we can say now O1 it's equals to, in this case, it's going to be 2 times K1. So that is what we have there. So that's where that comes from in that case, right? So that one we just said for us, we use an exterior angle of a triangle, we add them together. Thereafter, we know that these two angles are equal. Then we substitute in a space of T, we substitute K1. So that is the first triangle. Now let us look at the second triangle. So in the second triangle, we will say again O2, same thing that we did on the first triangle. Now we'll say it in this case, O2 is equals to what? It's equals to K2 plus P. Same reason, it is what? It is an exterior angle of a triangle. So in this case, we say O2 is equals to K2, so that angle there, plus angle P, which is the angle P there. Why? It is an exterior angle of a triangle. So that's what we have in that case. Now, proceeding into this, but again, we notice that we have equal sides here due to that radii. So because we have equal sides, we also form an isosceles triangle on the side. So we also form an isosceles triangle where the base angles are the same. So this is to say, we already now established to say K2 is now going to be equals to P. Why? Angles opposite equal sides. So because of these two sides are equal. Now, what we have in the following is, we can now say, because we know that O2, we already had our O2 as equals to K2 plus P. We know already that K2, we know that K2 is equals to angle P. That is to say, where there is angle P, I can replace angle P with what? With K2. So in that case, we'll have O2 is equals to K2 plus, instead of P, I now have another K2. Right. So what you see now is that O2 is now equals to 2 times K2. So that's what we have at the end of the day then. Now, so this is where that comes from. So I was just showing it to you there so that you know where that comes from. Thereafter, we now proceed. We know that plus O1 plus O2. So we just add them together to give us angle TOP. So our angle TOP is what? It's O1 plus O2. Now we say O1 plus O2. We know that O1 in this case is 2K1. We find that 2K1 there. That is O1 plus, this is O1 plus O2. Our O2, which is there, so our O2. Our O2, it was equals to 2K2, which is 2K2. Just showing there the circle and the square there. So that in that case, we are saying now, we can now factor out the 2. 2 is common. We factor out the 2. We remain within the brackets K1 plus K2. But remember, K1 plus K2, they make up the whole angle. They will add them together. They make up what? So K1 and K2, they make up TKP. So K1 plus K2 is TKP. O1 plus O2, it is what? It is TOP. So that's what those form. So this O1 plus O2, it forms as TOP. So that's what we're having in that case. So in a space of K1 plus K2, we can say it's TKP. And in a space of O1 plus O2, it is TOP. So now we have proven that angle TOP is equals to 2 times angle TKP. So to prove this, we needed to draw construction for us to be able to create the triangle that we can work with. So to prove this theorem, we need to work with triangles. So for this revision, I will only focus on the first that methods that are utilized there. However, we can still use the angles in a triangle as supplementary. Right. Let us move to question 8.2. In 8.2, now I will give you 5 minutes also to complete the question 8.2. Right. Welcome back, grade 12. Now, let us look at question 8.2. In question 8.2, we are told the following. In the diagram, O is the center of the circle. So, O is the center of the circle. The moment we have O as the center of the circle, all the center theorem comes in to say angle at the center equals to twice the angle at the circumference, maybe a tangent perpendicular to the radius. All of those are coming back. Given theorem 1 comes back to say the line from the center perpendicular to the chord bisect the chord. So, but let's see. O is the center of the circle. A, B, C, D is the cyclic quad. O, B, and O, G are drawn. So, we are told that A, B, C, D is a cyclic quad. So, the moment they tell us this, all the properties of cyclic quad, they come into play. Which ones? To say opposite angles, they are supplementary. So, we know that this angle A plus angle C, they are supplementary. They add up to 180. And angle D plus angle B, they add up to 180. And also, when we have a cyclic quad, we know we talk about the angles in the same segment. So we look for that angle in the same segment if they are there, but we don't have them there. And we also look for what? We look for an exterior angle of a cyclic quad equals to the opposite interior angle. So the moment they say cyclic quad, you list all of the theorems that are under cyclic quad. Number 1, we're saying opposite angles are supplementary. Number 2, we're saying angles in the same segment where we have angles subtended by the same chord. Number 3, we now look at the exterior angle of a cyclic quad is equals to the interior angle. So we look for all of the 3. We notice that only angles, which is A plus C, are supplementary. It's applicable in this case. Others are not met in this case. So we are told that if O1, let's just discuss the solutions now. We are told that in this case, if O1 is 4x plus 100. So O1 in this case is 4x plus 100. And angle C, it is what? Your angle C, which is here, it's what? It's x plus 34. So what are we saying? Calculate, given reasons, the value of or the size of x. So remember now, we are told that this is a cyclic quad. We are told that A, B, C, D, it's a cyclic quad. So these two are supplementary. So if we can prove that, we are okay. But we are told that O is the center of the circle. Now this is to say to us, now this is to say O1, angle O1, it's equals to, remember this one, it's gonna be angle O1, it's equals to 2 times angle A. Because angle at the center, so we can see that if we can do a bow tie there, you can see that this is the angle at the center. S equals to twice the angle at the circumference. Now we know that our O1 was given as what? It was given as 4x plus 100. It's equals to 2a. Then what do? We are looking for angle A. We divide by 2. Everything we divide it by 2. Or we just say multiply by 1 over 2. That cancels out. Then we have 4x over 2. It becomes 2x plus 50. That's our angle A. So that's where angle A comes from. So where does it come from? It comes from angle at center equals to 2 times angle at circumference. So that's why, or that's where that angle comes from in that case. Then we can now say, okay, angle A is 2x plus 50. So what do we now do? We can add A plus C to say angle A. So this is to say angle C plus angle A is equals to 180. What is the reason for that? This is the step I skipped there. What is the reason for that? Opposite angles of a cyclic quad are supplementary. So that's what we're having there. So angle C is what we have, it's x plus 34. So this is the angle C, x plus 34 as we have there, plus angle A. Our angle A is 2x plus 50. It's equals to 180. Then we solve for x there, and our x is 32. Right. We move on to question 8.3. Now for this question 8.3, I will give you 7 minutes to complete this activity. Right, welcome back grade 12. Now let us discuss the solutions to this activity. Now we are told that in the diagram, O is the center of the circle. OB is it's not a diagram, it's a diameter. Supposed to say diameter there. Of the smaller circle, so OB, it is a diameter. Already, the moment we have a diameter in this case, we can think of the theorem that says angles in the semicircle. We already can see that this is supposed to be 90 because this OB extends the angle M at that point there. Should AB of the larger circle intersect the smaller circle at M and B. Write down the size of OMB. Provide a reason. They even said write down, so there's no need for us to calculate. We can see that OMB, which is this angle, it's actually 90 degrees. What is the reason behind this? OMB is 90 degrees. It is angles in a semicircle. It is subtended by the chord. So this is subtended by chord OB or diameter. Sorry, it's subtended by the diameter OB. So it is subtended by that diameter in that case. So we write it down as 90 degrees. Now let's look at 8.3.2. Remember, we've established that this is 90 degrees. Right. Now they said if AB is 100 units, root of 300 units, so the whole of AB from there to there, it is root of 300. Then they said OM is 5 units, so OM, which is from there to there, it's 5 units. Calculate given reasons the length of OB. So they want us to find this length. Now how would you find this length? Because of this angle, we have a right angle triangle. However, we are told that they are intersect. This is 90 degrees. When this is 90, we have a center. We have a line drawn from the center perpendicular to the chord. So this goes to theorem number 1. So in this case, we are now saying, remember, our AB is root 300. When we simplify it, it's just 10 root 3. Now we are going to say in this case, therefore, MB is equals to half of AB. Why? Because line from the center perpendicular, it is perpendicular to the chord. It means it bisects the chord into 2 equal halves. So the half of root 300 is what? It's 5 root 3. So what we now have, we have two sides of a right angle triangle. Now we'll say OB squared is equals to OM squared. Looking at this right angle triangle now, plus MB squared. Plus MB squared. Why? This is Pythagoras theorem because this is a 90 degrees. So it's a right angle triangle. Then we find that OB. So we have OM as 5 squared. And we have MB as 5 root 3 squared. Then our OB is 10 units. Right. Now let us move on to 12. Now let us look at question 9. Question 9, it is worth 9 marks. So I will give you 10 minutes to complete this question. Right, welcome back grade 12. Now let us discuss the solutions to this activity. So we are told that in the diagram ABCD is a parallelogram. The moment they say ABCD is a parallelogram, all the properties of parallelogram they apply to ABCD. We know that two opposite sides are equal and they are also parallel. Right, with AB is equals to 14 units and AD is produced to E such that AD is to DE equals to 4 is to 3. AB intersects DC in F. and EB is equals to 21 units. So what are we supposed to do in this case? They said calculate with reasons the length of FB. So they want us to find FB. This is the length that they want us to find. Now, what do we know about these two triangles? So what we know that is the following. We are given the ratio AD, it's 4. So we can just say it's 4 and 3. Now when you take the ratio and you put it in the diagram, you must convert it into a length. When you convert it into a length, that means this AD is 4P. For P is just any letter. You can say 4X, you can say 4 whatever, any letter or any variable that you want to use in that case. So when you say 3, the 3 there. So when the ratios have the P and this, those two, they are now our length. So we are told that EB is 21 units. So from there to there, it's how much? It's 21 units. So we are told that that is 21. That means from this side, again, to this side, it's how much? 4 plus 3. So that's how we do it. Remember, when I'm moving the ratio into the diagram, we attach a variable to it so that the ratio now, it becomes the length. Now, when we move forward, we are told that we know that according to proportionality theorem, we're saying, okay, because I'm looking for FB, I'm going to take the same shape. So FB, it's equals to DA, which is the same thing that we have here. So we'll say FB, it's equals to DA. So I'm just making the same shape. So under proportionality, you must make the same shape. Then when you check again, it can be all over. FB can be over EF. If it is over EF, that means we're going to say under the DA, under our DA there, we'll also say ED. But that won't help us because already we're given that this is 21. So I can rather say, if I say it over EB, that means it's equals to, I must do the same thing. So if I went from that to that, I must do the same thing on the other side. So that means we must just follow the same shapes. So whatever shape we have, we create it on the other side. It's equals to EA. When I say the same shape, check. So you can see that it's 1, 1. So the same thing, we just say 1, 1 again. So it will not be correct if you now say this, maybe just do it like that. Then on the other side, you just do it the other way around. So it must be the same way. If you said FB, that means that side is corresponding with what? With DA. And EB is also corresponding with EA in that case. Now, what do we do from here? Then from this statement, we're saying, okay, I don't have FB, so it's FB over EB. What is EB? EB is 21. It's equals to DA. DA is 4P all over. Then we have EA. EA is 7P. Then what do we now do? We cross multiply. We find that FB is equals to, or we can say multiply by 21 over 1, 21 over 1. So remember, 4P and 7P, P and P will cancel out. We'll have 4 over 7. 4 over 7 multiplied by 21. When we multiply by 21 both sides, then FB, it becomes how much? It becomes your 12 units. So P and P will cancel in that case. Right. Let's look at 9.2. They said prove with reasons that triangle EDF is similar to triangle EAB. How do we prove similarity in this case? Now, in this case, what are we going to do? Let's check. So we are told that we want to prove that triangle EDF, which is that smaller triangle, it is similar to triangle, the bigger triangle, that bigger triangle there. So how do you prove that those two are similar? We now look at the first thing. If we can check, number one, angle E is equal to angle E. Why? Angle E is common. So this one is common because it exists to both triangles. So E, it is falling under EDF and under EAB. So it is common. Number two, we notice that these angles are equal. Why? Because we have parallel lines. Remember, when we have parallel lines, we have fun. We must have fun. So we must have fun. That's my friend right there. So when you have fun, we look for corresponding angles, cointerior, and we just write by n there. And we look for alternate. What we see now is these two are parallel. Then we can now see that this is corresponding with that side. So that's why we say we are having fun in this case. So EDF So EDF, which is this angle, is equals to EAB. Why? Corresponding angles. Because of DC, it's parallel to AB. So that's what we're told initially then. Then therefore, if now we have E1, these angles and this angle is equal, these two are equal, therefore this angle must be equal to that angle. That is a third side of a triangle. Now if those are equal, we have angle, we proved an angle, angle, angle. So that is our similarity that we have proven there. So we're saying angle, triangle EDF is parallel to what? EAB. How do we do it? It's easy. Remember, we have written angle E is equals to angle E. So we'll start by saying E, it goes with E. D, from that triangle, it goes with A. Remember, the one in the middle with A, small cap there, is the one that we're using. Then we're saying F is the one that we're concerned with. Then it also goes with what? With B. Then we can say these two are similar in that case. Right. Now let us go to the next question. Now, when you're looking for the next question, they say calculate the length of FC. But we must remember one thing. We already established that a triangle, let me just go back. We have established that triangle EDF is similar to EAB. So we know that triangle EDF is similar to EAB. So we have proven that already. Now, what we can do there, we can just create a smiley face. We can now write this in ratios. We're now saying, to write this in ratios, we'll have the following. We're now saying E goes with that, we have ED. So if we have ED, it's equals to, we have ED all over EA. We create the same shape here, EA. It's equals to, we come again, we create another shape there, DF. It's all over. It's over what? AB. So you see the shape must be the same. A, B. It's equals to, again, we now create a smiley face there. So we can see now it's EF over, same way, create the same shape again, EB. Where does this come from? This comes from the similar triangles. So that is the statement that we've used there. Now, we are looking for FC. So FC is them. So for us to find FC, it is best that we can find DF. We have the angle DF, it's in our similar triangle, and we are told something about AB. We know that we're told that AB was 14 units. We know that we can find DF in that case. And again, remember, we have, this is 3P, this was my 4P. So this is from the first question, this was 7P. Now, what you can do now is the following. We are looking for FC. FC falls on DF. So whenever there's a DF, I'm going to use where there is DF. Can use DF. So this AB over DF will come into play there. That's what we're using there. And we use what is given also. We know that ED, we have ED is given, and we are also given what? EA. So ED and EA are given. So we have ED and EA. So these are given as 7P and 3P. So we're now saying DF. So this is just DF over AB. It's equals to, in this case, ED over EA. Right. So we now know that our DF is what I'm looking for. Why DF? Because I want to know what is FC. And we're doing that because DC and AB are equal. Right. Then we now know that our AB, so is DF over AB. What is my AB in this case? AB, it's A. B, it's 14. It's equals to, we have ED. ED is 3P. We have 3P then. All over EA. Our EA is 7P. Right. So those are the two that we use there. Then when you cross multiply, we get DF is equals to 3P over 7P times 7P. Then we find our DF as 7 units. Good. Now we have DF is how much? It's 6 units. However, you must remember that DC is equals to AB. Why? These are opposite sides of a palm. parallelogram in that case. Right. So this is to say, if we're saying that, but DC is made up of DF plus FC, it's equals to AB. Now we know that our DF in this case is 6 plus FC, it's equals to, what is AB? AB is 14. Then we transpose the 6 to the other side, or minus the 6 both sides. Then FC is 14 minus 6, which is 8. So that's why we get the 8 units there. So it is 8 units. So that's how we got that answer in that case. Now, let us look at question 10. For question 10, the 12th, I will give you 12 minutes to complete this activity. Welcome back, grade 12. Now, let us look at the solutions to this activity. They said prove with reasons. Okay, in the diagram, PQRS is a cyclic quad. So when they say PQRS, RS is a cyclic quad. So that is a cyclic quad. That means the properties of a cyclic quad comes into play. What are they? Number one, an exterior of a cyclic quad. Number two, we have angles in the same segment. And number three, we have the interior angles of the cyclic quad are supplementary. Now, let us now go through this one. We are told that in the diagram PQRS is a cyclic quad. So this is a cyclic quad. So that is a cyclic quad. Like I said, three of them exist. Number one, we're saying the exterior angle of a cyclic quad. You think about it, we can write it down on your question paper. Number two, we can think of what? Angles in the same segment. Number three, we can think about opposite angles are supplementary. Through P and R, they meet at A, tangent at A. So we have tangent that are meeting at the same point. In that case, the tangent to the circle PRN meet QS produced at A. RS is produced to meet AP at B. So that's why they are created. Those are the tangent that we're having. PS is produced to meet tangent AR at C and PR intersect at M. Prove with reasons that S3 is equals to S4. So what we can do there is the following. Remember we talked about a cyclic quad. So let's apply those properties of a cyclic quad. When you apply them, you can see that this is subtended them. We can now talk about this angle being equal to that. Why? Because the opposite angle of a cyclic, or the exterior angle of a cyclic quad, equals to the interior opposite angle. So we can let this one be x, so that angle will also be x in that case. Then what else do we know about this triangle, or about the cyclic quad we have in that case? Now, when you look at the two again, so what else, which other angles are equal to S? So what's important in this case is that we fill in all the angles that are equals to S. We are told that, remember we are told that PQ is equals to PR. So these two are equal. When these two are equal, that means these angles are equal. That means this is also X. So that's what we have in that case. Let me just go too far until here it's equals to X. So we know that those two are also equal, and this is X in that case. Right. Then when we proceed, we can check all other angles that are equal to X. So we can have the 10 chord theorem there. We can have that angle, all of it being equal to X. We can have, this is the cyclic quad again. Let's explore all of the properties of the cyclic quad. We can see that this angle and that angle, they form a bow tie nicely there. This is also X. I'm just gonna make a dot, show a dot there to show that those are also equal in that case. So those are ways we can do all of that one. We can populate the diagram to have all the x's that we can find. This is 10 chord, we can have that as X again. So those are the things that we can do. So first thing that is important for us, work with the diagram, find all of the angles that can be equals to X before you can proceed. Even this one will be X, 10 chord theorem again. This X will be R1 plus R2 in that case. Right. So that's what we can have as X in the in those questions. Now let us now go to the proof. They said prove that S3 is equals to S4. I just intentionally made S3 to be X because that is what I'm gonna work with in this case. Now what are we gonna say? we're saying S3, our S3 here, it was equals to PQR. This is the first thing I said. S3 is equal to PQR. Why? It's an exterior angle of a cyclic quad. So the cyclic quad, we had them. So these angles are equal from that cyclic quad. Second one, we know that R3 is equals to PQR. How is R3 is equals to PQR? These two are equal because of this triangle there. So opposite side equal sides. We are told that these two are equal. We are told that PQ is equals to PR. That is why we can say equal sides, opposite angle. But because PQR is equals to S3 equals to PQR and RT is equal to PQR. When we have a situation whereby two angles are equal to the same angle, then we can say those two angles are equal to each other. So that's what we can say. We can therefore say S3 equals to R3Y because both are equal to PQR. Now, if we can say that, but we know that S4, we have mentioned that S4, you can see our S4 was X here. So we can go back to this X to say S4 is equals to S3Y, angles in the same segment. That's the bow tie we have there. That angle and that angle are in the same segment. When you just create the bow tie, you will see that. Now, then angles in the same segment. Now, we can now say, because S4 is equal to R3, now in the space of R3, I can put S4. Then when I put that, it's S3 is equals to S3 equals to S4, which is proven in that case. Now, let us look at the second question, 10.2. Prove that SMRC is a cyclic quad. So it's SMRC is a cyclic quad. How would you prove that that is a cyclic quad? Remember, cyclic quad, we apply all of the properties of the cyclic quad. We can prove, if we can prove that this angle is equal to that angle, which is an exterior angle of a cyclic quad, then that is a cyclic quad. So we are done there. That is all we need to do. Prove that is equals to that, or we can prove that angles in the same segment, or we can prove the contrary opposite angles are supplementary. So what are we doing? Remember, ARP, we mentioned that already, is equals to PQR. It is the 10 chord that we did on the first diagram. So it is that 10 chord theorem that we did there. Again, we established that S4 is equals to PQR again. We proved that in 10.1. So S4 is equals to PQR as proven in 10.1. Therefore, because ARP and S4 are equal to the same angle in this case, then S4 can be equal to ARP. Both they are equal to PQR. So we've proven that already. So that's why I said go and make sure that you do what you populate all of the values that are equal to X. And remember, this was also X. So we are working with this part. We're interested at this part. Already that we have established those two. Then therefore, SMRC, it is now a cyclic quad because of these two. Why? Converse of the exterior angle of a cyclic quad. So this is what we proved, that this the S4, which is S4, also S4 there. So the cyclic quad is extended in this way. It's extended to that way. It's equals to the R1 plus R2 in that case. So we are done. So all we need to do, we have that SX, we have this SX there. And we showed that this was 10 chord from the previous question. Now, let us look at the solutions to the last question. We are told that RP is a tangent to the circle passing through. Prove that RP is a tangent to the circle passing through P as at A and P. So triangle P, so there is a circle there that is passing at S, okay, it passes at P, so we have a circle there. So we need to prove that RP is a tangent. So what is RP? RP is a tangent. So how can you prove that RP is a tangent? We can simply use a tangent perpendicular to a center, but we don't have a center, that is out. 10 chord theorem, we can use it because we have a chord and we have a triangle. So if we can check, if we can prove that those two are equal, using the 10 chord. So those two, P2 must be equals to A2. That's why we're going to use what we call 10 chord theorem. So that's our aim. Our aim is to prove those two. But how can we prove these two? We notice that P2 is in a different triangle and A2 is in a different triangle. So what do we do in this case? We now have to make sure that we can connect the two triangles together. So we can see that P2 is in this triangle and A2 is under other triangle, which is this one there. Right. How do you connect them together? We can connect them using the exterior angle of a triangle. So we can extend that to become the exterior angle of a triangle for this one. So that is to say, in triangle PRS, in triangle PRS, we can now say we have S3 is equals to what? It's equals to P2 plus R2. Why? This is an exterior its exterior angle of a triangle equals to the two sum of interior angles. So exterior angle of a triangle. So that is exterior angle. Hope that you can see. So here I'm trying to write exterior angle of a triangle. Then we can also check, okay, however, if I produce this line again, in this case, I can prove that S4 is also equals to what? It's equals to angle A2 plus P1. Also, this is the exterior angle of a triangle. So this is exterior angle of the triangle. So I'm just gonna say this is X, this is W. So I just wanted to show you. So using that two, this one and that one. So those are the two that I've used. So I've used two triangles to prove in that case. So the formal proof will say S3, our S3 then, 3. So our S3 in this case. So I'm just gonna show that nicely for us then. Right. So we'll just prove that S3 right. Remember I said to us we need to prove that these two are equal. So they are in different triangles, so we're using that triangle and we're using the other triangle. So I'm gonna use a different color for the second triangle so that we can see which triangle we are using. So we were extending that line there to have the triangle. So what we have in that case, so the other triangle that we work with is this blue triangle there. Why these two triangles? Because this is the angle that I'm interested. I'm interested in A2 being equals to P2. Then I'll be able to prove this is a 10 chord. So we can prove 10 chord using those two. So I will just prove those two, and this is extending to that line. So that's why I'm saying S3, which is this, is equals to R2 plus P2. Why? External angle of a triangle. However, S4 again, as I've showed them, it's equals to what? It's equals to P1, which is P1 here, plus P2. So those are the two that I've worked with. So this is equals to that and that. And this one is equals to that and that. Right. We now proceed to say, okay, that is what we have. But we know that S3 is equals to S4. Why do we know that? It's proven in 10.1. So this was proven to us in 10.1. So after that we've proven, we know can equate the two now because these two are equal from 10.1. When you equate them as R2 plus P2 is equals to P1 plus R1. However, what you notice that is that from the initial point that this side, it was equal to this side, the 10 chord theorem. So if we use this as a 10 chord theorem, we notice that P1 is equals to R2. So you can call them Y and Y. Those two are equal. Y is the tangent AP from on the bigger circle. So these two are equal to each other. So when those two are equal, that means in a space of, I can replace my, what did I do here? Okay, let's just go back to that. We have R2 plus P2 is equals to P1 plus A2. Right. So what is happening is I can replace my R2 with P1, meaning I can just have a situation whereby I have P1 instead of R2, because we said P1 equals to R2. That means I can put P1 in a space of R2 plus P2 is equals to P1 again plus A2. Then what do we do? This A will be minus by P1 both sides, or transpose it. This 2 will cancel out. Then P2 is equals to A2. Then we proven that P2 is equals to A2. Therefore, RP is a tangent to the second. So the easier way to do this one, what we're supposed to do, identify which angles are we supposed to prove, or we can try to prove. We can prove that P2 is equals to A2. Now, to prove that P2 is equals to A2, check which triangles they belong into, or the shape that they are in. They had two triangles. Then look at the relationship between the two triangles and see if we can move from one side to the other. How do I do it? I will now use the triangle that has A2 and the triangle has P2. So that's what we do. We use the triangles that have the sides that we're trying to prove. Then you can follow the proof as we did in that case. Right. Then we can say RP is a tangent to the second. Y is the converse of the tan-chord theorem. So we have a tan-chord theorem now. So we have a tan-chord theorem at that point. All right. Now, thank you, grade 12s. Enjoy the rest of the day.